All right, good evening, everyone. We're going to get started, if that's all right. Seems like it's all right. So, first and foremost, welcome to the LA Python Data Science Meetup. Glad to have all of you here. A few points of order. First and foremost, I wanted to thank our sponsor, OpenMail. We're in this awesome space. I also wanted to, there's usually a couple of questions come with meetups, and they're, parking is a question, where the restrooms I just found out is a big question, and is it being recorded? And yes, Carl is recording it for us, and we'll be putting it up on YouTube.
Thank you, Carl.
Sending me a link, and I'll post it on the interwebs. So let's get right to the talk. So we've got a pretty great speaker. I'm pretty psyched. He flew all the way down from sunny Seattle to be here with us. Carlos is the CEO and founder of Dato, formerly GraphLab. This is a company that's been around since it started as an open source project in 2005, I think. Is that correct? 2008? Still a long time. And they build a whole bunch of tools. Basically, they have a workbench for data science. Right here, gotta represent. So I got to know more about their product line at O'Reilly Strata Conference, and I got to talk to some of the engineers. If you've ever seen me talk, I'm really into columnar data stores, and we got to talking about their columnar data store product, and it was just really good, knowledgeable folks, and he was willing to come down here and give us a talk. I think that about covers it. All right, well, let's welcome Carlos Guestrin.
I get that t-shirt, I want one. Let's see, let me know if sound is okay. Is it okay from the back? Yeah, good. So really appreciate being here. It's pretty exciting, nice setting too. I'm looking forward to checking out the art afterwards. And I'll talk a little bit about some challenges and opportunities of machine learning in production and at scale. So I've been doing machine learning for about 20 years now, and if you talked to me in 2012, here's how I thought about machine learning. You start with some data, and you do some machine learning thing with the data, and then I show that my curve is better than your curve, and then I write a paper about it. And the world has changed a little bit over the last 3 years, and today industries are being disrupted by machine learning. So you think about the number of intelligent apps that are being built, they use machine learning, and they take industries like taxi industry and completely break it apart. It's pretty exciting. So instead of being this esoteric thing, now we're at the core of new technology. And the timing is really great because over the last decade, companies have spent time and money putting the data into one place and spending money on database systems and not getting enough value out of that. And then over the last few years, they've been trying to do basic analytics with basic tools. And that allows you to answer questions like, what fraction of my customers are churning, but not why Eduardo is churning and what I can do to stop Eduardo from churning. Don't churn. And so this is where machine learning comes in. It allows you to build intelligent applications and make predictions in real time. So these are things like recommender systems, fraud detection systems, ad targeting, personalized medicine, and more. And what I'm very excited about is enabling this technology to be deployed at scale in real time in production. So today, as I think about the path of what it takes to build such technology, usually you start with an idea. I call that inspiration. And even though you think you start with algorithms and math, you usually start with what's called data engineering. Cleaning your data, put it in one place, and eventually you bring in the machine learning side, which in a marketing speech I'm calling data intelligence. And this is really an iterative process that goes between the two. And finally, you want to deploy this in production so it affects your customers in real time. So if you think about this pipeline, on the left side, the inspiration doesn't happen inside of a Hadoop cluster. It usually happens in a coffee shop with people like you using simple tools like Python or R. And eventually you have to translate these things into scalable, elastic systems that maybe live in the Hadoop ecosystem. And that process is painful, slow, time consuming. So for example, very few people go home and say, honey, I had a great day, I cleaned a bunch of data. So that process is slow and honestly quite painful. It's hard to deal with the large amounts of data when you're trying to set it up. The machine learning part can be hard. Often folks don't have mathematical background that requires to read papers, and maybe it's hard to take those things at scale. And when you want to deploy a real-time system that within milliseconds give you predictions of whether a transaction is fraudulent or not, you have to build yet another system that takes time, it's slow, and brittle. And so these three challenges led us to think more about what we can do about them and about the opportunities. So the opportunity is to take these three areas and make them both scalable and simple at the same time. And so the question is, what does it mean to make them simple and make them scalable? So let's start with data engineering. So what we need is tools for data cleaning and feature engineering, which are basically straightforward. Easy like pandas, not hard like Hadoop. And yet, we want to be able to deal with terabytes of data. And these are tasks which are mostly called data parallel tasks. So let me dig into that problem. And at the core, what we've done is worked on scalable data representations that allow you to deal with tons of data in a pretty simple way. And here we use columnar stores, as Eduardo was talking about. So, for example, what can you do with an optimized out-of-core columnar data frame? Well, you can take 20 billion ratings and make a recommender system. Or you can take a graph of 128 billion edges and run PageRank on it, on a single commodity machine. No need to go to clustering. I'll show you that in a few minutes. I'll actually do some live demos today. I'll do about 5 live demos. So how? So usually I think about data as rows. User recommended a movie with a particular rating. But most data engineering transformations we want to do involve columns of the data. So let me give you some examples of this. So this might be Netflix data. So maybe a transformation I want to do is take, and I have some Python code examples here which you may want to read. But maybe the first thing I want to do is normalize that ratings column, divided by the sum. So that just takes one column of the data, computes its sum, and then divides every element by it. Maybe you want to create a new feature. Maybe you believe that rating squared is the way to go. If I introduce rating squared, I'm going to change the world. So basically, I want to take that ratings column and apply a square function to it and create a new column, rating squared. Or maybe I want to select a subset of those columns and feed it to a learning algorithm that's going to make some prediction. So feature engineering is columnar. And because of that, we developed S-Frame, which is a scalable tabular data structure that is out of core, so it runs on disk, is highly optimized and compressed, and it behaves just like pandas, but scales to a tremendous amount, both on a single machine, as I'll show you today, and a distributed setting with the same Python code. So we'll show, as I said, we'll do several demos, but at the very core, just so that you understand, is how that data is laid out on disk. So we think very carefully about how we lay out our data. We structure it in shards that are not necessarily aligned across columns. So this is why the pictures look a little different here. And we use all sorts of compressing schemes that are adaptive to different data types. So if you take a Netflix data set, which has 100 million rows, 3 columns, it's 1.4 gigs raw. If you gzip it, it's about 289 megs. But if you use a columnar store like this to represent it, this is what happened. The user data compresses down to 176 megs. The ratings data compresses down to 47 megs. And the movie rate data compresses down to 256K. And so the total is actually even smaller than what gzip can do. And it only takes a few seconds to take your data and write it from raw file into a columnar format. And the columnar format really has a lot of impact. So let me show you some demo. So this is the first demo of the day. Hopefully everything works. That's the second demo of the day. Okay. So there'll be a lot of Python today. I hope that's okay with you guys. I heard this is the Python Meetup. How many people program in Python? About 70%. Or maybe more. So we've implemented this with a system called GraphLab Create, so you can import GraphLab Create. I'm not going to go line by line, but I'm just going to tell you what's happening. So import GraphLab Create. Oh, I should upgrade to version 1.4, the release on Monday. I haven't upgraded yet. Sorry. And I'm going to read some bio data set. So this is some biological data, and it's used to predict the viability of life. So let me show you what that data looks like. First, I'm going to show you the number of columns and number of rows. We're talking about 950 columns, and read carefully here, 931 million rows. And this is running on a single machine. So this is about 1 trillion cells, which without any compression, maybe it's like between 4 and 10 terabytes a day. But of course, we compress it and think about it very carefully. And this is running on a single machine. So let's take a look at this data. So the first thing I'm going to do is just show you the head of the file. So this is a bio data set, and it has a column Y, which has to do with the viability of life. It's either +1 or -1. So based on some mutations of a gene, RAF-A, RAF-G, and a bunch of these, you're going to predict whether life is viable or not. So -1 or +1. And you see some of these are binary, 0, 1, and some of these are floats. So for example, -1.006. So I won't do the machine learning side on this data set. I'm going to use a different data set, but let me show you a few things that you can do for columnar store. The first thing that you do, let's do the slowest, not the slowest possible, the most annoying operation a columnar store. Let's look at a particular row of that data. So now you have to go column by column and extract that row. Not so easy, but it's pretty fast, even though there's 10 terabytes of data stored. So you see there's a lot of zeros, ones, there's some, and if I scroll down, there should be some numeric values, 2.2, 9.0, and so on. So here's a question. 931 million rows. I'm going to take column Y, and I'm going to compute its sum, and I'm going to time it. How long is this going to take? Okay, let's see. So 2.25 seconds. Not bad. I feel pretty proud of that. By the way, the sum is 800, in case anybody was wondering. Let's take another column here, which is how much is your gene related to a primate gene. If you want to offend somebody, you say, your gene just looks like primate. It's all floats. How much does it take? How long does it take to sum a column of 930 million floats in this column store on a single machine? 2.05 seconds. Not bad. We actually have a data visualization tool, so you can type .show on anything. I'm going to show you in more detail a little later, for the interest of time. But here's what I'm going to do. This is feature engineering. So I'm going to create a new column called my column, which just takes column A, C, G, and T, random columns, and adds them together. So you might want to do this in feature engineering. So how long does it take to take these 4 columns, 930 million rows, and add them together? And then I'm going to compute its sum. So new columns being generated, and this out of core, so it's all in this because this machine doesn't have that much memory. And it takes 8 seconds to create a new column. And now I can show you other things, but I want to show you a lot more today, so I'm going to stop there and just say the columnar representations for your data out of core, way to go. And you can download it and use it right now. Behaves just like pandas, but scales to terabytes of data in a distributed setting or just in one machine. So let's jump into the some performance curves. So I was asked, I was trying to get a wine about how does it relate to some of the systems out there. So here's a benchmark that was run not by us, but some of the folks that use Spark, and they compared a particular task on some Twitter data from 2010. So this is a graph with 1.4 billion edges, and you try to run Spark, GraphX, Giraffe on it. The best one takes about 200 seconds. With what I just showed, it takes about 70 seconds to run pager. Correct component section. But this is not the whole story. These other systems required 16 machines while I did this on my desktop. And then in terms of scaling, just raw scaling, I was trying to figure out what I can do on my desktop. The Common Crawl graph is the largest publicly available graph out there. It has 3.5 billion nodes, 128 billion edges. Lots of systems have been tried on it. They typically don't even run, even on a cluster. We can run PageRank on this, 9 minutes per iteration on a single machine that has an SSD. So that's how we think about data engineering. So fast, out-of-core, columnar representations that allow you to take your laptop and deal with terabytes of data. Let me talk about the machine learning side. This is the data intelligence side. What does it take to make machine learning scalable and simple? So we're back to our table. What I want is machine learning algorithms that are available even for non-experts. And this is not about terabytes of data. People are obsessed about, I have 10 petabytes of data. No, my data is bigger than yours. In machine learning, it's about computation-intensive procedures that need to iterate over your data again and again and again. And these are not typically data parallel, so they can be much harder. So how do you scale that? So we've been focusing on robust machine learning algorithms that build on S-frames and the graph version that we call S-graph, and scale to big problems. So in terms of simplicity, we've been thinking about a hierarchy of types of users. If you're a hardcore data scientist, maybe you want to use roost decision trees or deep learning or LDA, choose your own algorithm, or even implement your own using the SDK. Maybe a savvy developer might be interested in just calling a regression algorithm that automatically picks and optimizes the parameters and models of the underlying algorithms. Or maybe somebody would like to just build an application that's a recommender system and doesn't really care what thing is going underneath, but you just want it to work at scale with your data. So we built this hierarchy of machine learning tasks and algorithms where you can choose where you want to start and you can drill down. So for example, you can just call recommender and then you can decide, no, I want to build my own, or I want to use a particular algorithm, and you can iteratively improve that solution. And I'll show you a demo of that a little bit later. But before that, let me dig into one of the algorithms that we've optimized, which is a deep learning library. How many people have heard of deep learning? Latest buzzword in the world? So this is a reinvention of something called neural networks. And so I'm going to talk about that, but before I do it, I'm going to show you a second demo. So, and this is about usability. So here, let's see. Okay. So I'm going to see this. So we took 1.5 million images, labeled with 1,000 different categories, and trained a deep neural network using a GPU. So we have, within GraphLab Create, we have deep learning on GPUs as well. And then we took that learned model and deployed as a service on AWS. They can query by sending images up there. So every time I click on an image, it goes to this service on AWS which has GPUs, makes a prediction, and within some 100 milliseconds comes back with an answer. So for this image over here, it makes a prediction. Paper towel, that's good. Let's pick another one here. So for example, this one over here, so it gets uploaded to AWS, comes back for prediction. We heard it says pick or acoustic guitar. It's pretty good. Let's see another one. How about this one here? It says sends up to AWS, comes back for prediction. It says, what does it say? Chime. That's pretty cool. But these were all images that were part of the original ImageNet data set that was used to train this model. Let me show you an image that was not in that data set. Click this one, send it up, comes out with a prediction. It says Labrador Retriever. This is my dog. This is the lab in GraphLab. So it works pretty well. Now I want to tell you what's really cool about this demo. So we launched 1.0 of the GraphLab Create product around late October of last year. And a week before, we're really busy, a week before, new front-end developer Dick joins the team. And he says, what should I do? And we're all too busy. And so say, oh, why don't you play with the product and just build something just to learn how to use it. He doesn't know anything about machine learning, never used GraphLab Create before. He knew Python. He built this in a few days. Pretty cool. So let's talk a little bit more about deep learning. About that. So, and I'm going to talk today just about deep learning computer vision, but we can talk about deep learning in other domains and what it is, and why it's had a lot of impact. So, what does it mean to make predictions in computer vision? Let's say that I want to predict that this picture of my grandmother is a face. The way computer vision works is you have these little detectors, which intuitively you can think about as detecting a nose, detecting an eye, detecting another eye, detecting a mouth, and then you combine this together, and if enough of these fire, you say it's a face. Of course, it's not as exact as that. Usually these are features that need to be created to analyze the image. And for decades, there's been a cottage industry of hand-tailored computer vision features. Famous one was SIFT, and then lots of came after that. The problem is, these were hand-tuned. It took a long time to build them. People got PhD theses for designing them, and a PhD thesis for designing SIFT2 and SIFT3 and so on. And it was quite a laborious process. What the folks in the deep learning neural network have been able to do is take the raw images and instead of extracting features that were manually designed to be able to make a prediction whether this is a car or not, so in this imported image, I do some extraction like this and then predict it's a car. Because it's so painful to design them, they build a multi-layered model that tries to automatically learn these features from data. So they take a lot of images of cars and try to automatically learn things that are useful for predicting this image as a car or not. So here's an example of a 3-layer neural network. So on the leftmost is detecting these little things, which maybe looks like a clown or something. But if you know a little bit about computer vision, anybody know what this means? They detect. So this detects an edge to the right, an edge horizontal, an edge to the left, and so on. And this detects what colors of this one edge. So that's what gets learned in the first layer, which is cool. In the next layer, you learn things like detect circles, detect stripes, detect color blobs, and so on. And in the third layer, you learn wheels, bumpers, steering wheels, maybe this is a bird beak, and so on. So each layer of the neural network is creating little detectors, like I talked about, the nose detector and so on, at different scales of resolution. So little edges in the image, circles and patterns, rectangles, all the way to wheels. And these are done automatically as opposed to hand-tailored features. The problem is a successful deep learning model looks kind of like this. It has 34 layers that were hand-designed by somebody, and another 2 PhD theses went into this. So the question is, how can you make this easy? So let me first show you what you can do with it, and then I'm going to show you 2 ways to make it easy. So what can you do with it? With this latest results, they've blown pretty much all these hand-tailored features, all these other things out of the water. So, and it started with some easier tasks. So for example, from images, detecting traffic signs. So where are the images of traffic sign? With 99.2% accuracy. That was a pretty cool first result. Another one is from Google. So if you see Street View, it tries to automatically detect what is the house number associated with a particular piece of image. And that gets 94.3% accuracy. Do you know how they achieve the other 6% of accuracy? Captchas. So if you go to CAPTCHA these days, it doesn't give you a random piece of text. It gives you a little image that looks kind of like this. You're fixing the neural network. Thank you very much. Not to me. They thank you, probably. Or not. So this was a result. But then, this really complex network with 60 million parameters that was hand-designed by some folks in Toronto won the ImageNet competition, which is a large-scale computer vision competition. And it blew other things out of the water. So this is an error plot, lower is better. And these are the hand-tailored features and the methods that were winning the previous years. And this was the neural network. And you see there was a big gap. The performance increased by a lot, like 17% here and 10% here. It really blew everybody away. And you can use it for other things. So you can use it for image retrieval. So if you give me this image, find me similar images. I'm not sure examples of that. And even what's called scene understanding. Even an image, say that this is the sky, this is mountain, this is grass, trees, and so on. Pretty cool stuff. So it's exciting. Let me show you a demo of how you can first use it. So I'm going to again do some Python code. So let's zoom in. Is that okay? So this is our deep learning library in Python, and we're going to use it for car detection. So the first thing I'm going to do is load some car training data set, and let me show you. I should upgrade to 1.4, thank you very much. And let me show you what the data set looks like. Some images are cars, some images are not cars. And you're trying to figure out which images have cars. So with GraphLab Create, you can call GraphLab.neural classifier.create, and if you're training data, and we'll create one for you automatically. Now, we'll optimize an architecture for you, those layers of the neural network, or you can choose your own. In this simple example, remember I talked about different layers of how you can use the system? At this level, I'm going to let it automatically pick one for me. So if I press enter, it's going to take this data set, which is relatively small, and build a convolutional neural network that's at 7 layers. And you can see uses convolution layer, max pooling layer, flattened layer, blah, there's a bunch of layers. And it just trains it, and now it's done. And on this data set, it gets about 98.6% accuracy, which is pretty impressive. So let me show you some of the predictions it makes. So these are the things that are least likely to be cars. So I'm going to go through all the images, sort them, and find the ones that it thinks are least likely to be cars. Thankfully, none of these look like cars. Can you see okay from back there? So there's a helicopter, there's some things over there, and yeah, least likely. Then let's see things that it thinks is most likely to be cars. And hopefully these are all cars. We just trained it, and it looks like cars. Yay! And now, let's see the misclassifications. So these are the things where it predicted, it predicted to be cars, but turned out not to be cars. And it's just going to give me a couple of examples. And this is some examples. I'm going to make it a little bigger. So you can actually see the examples. So this one, I used to ride motorcycles. They're not cars. But this one, if you squint a little bit, it looks like maybe the shadow looks kind of like a car. So it kind of makes sense. And we built and trained a neural network, deep neural network on the fly right here. So that's kind of exciting. And so in terms of performance, we use GPUs to optimize it, and it's really fast. So this is throughput numbers of images processed on a particular data set. And we took the benchmark from H2O, which is a machine learning package. And it's a distributed one, and they're using 63 machines to train the data, and they can process about 23,000 images per second. Here I'm using a GPU on a single machine, and I can process about 26,000 images per second. However, deep learning is not without challenges. So, on the pro side, it enables you to learn features from data instead of hand-tuning it, and it gets impressive performance gains on computer vision tasks, on speech recognition, on text tasks, and it has potential to have a lot of impact. However, there's some cons. So here's what a deep learning workflow typically looks like. You start with lots of labeled data, lots. You split it, let's say, 80-20 on something that you're going to use to train your model and something you're going to use to test your models. You learn this neural network, takes a long time, so that demo that I gave you of the deep learning model of the ImageNet 1.5 million images takes 2 days to train. Then you compare the validation set, and what do you learn? Yeah, but what's the conclusion, typically, first time around?
Doesn't work.
Doesn't work. So you go and you try again. You train some parameters, you add a layer, you remove a layer. You try again. 2 days later, you try again. And this is another kind of annoyance. So, there's 2 problems with what I talked about. Lots of data, and try again, and slow. So even though it has a lot of potential, it's computationally expensive, requires lots of data to have high accuracy, and there's a lot of things to tune. And you basically need a PhD to be able to tune those well. So something that's computationally expensive and has so many choices really means it's incredibly hard and boring to tune. So what can you do about that? Well, well, the way that we've been approaching this, to try to make it more accessible, is to provide what we call deep features. So this is a combination of two things, deep learning that we talked about here, and something called transfer learning. So let me talk a little bit about that. So remember how I talked about you take some input data and you use some of these hand-tailored features to predict whether it's a car or not? These features here is kind of generic. They're not specific for a particular task. They were devised in somebody's PhD thesis. Can you do the same kind of thing with a neural network? In other words, instead of using hand-tailored features, can you use features from a neural network that you learn on lots of data to train another model? That's called transfer learning. So transfer learning is you start with lots of data. For example, a neural network, you train a neural network just for that. You get great accuracy on the cat versus dog task. And then you take a new task, maybe you have 101 categories, and you take just the features, not the cat versus dog detector, but the features learning that inside of the neural network, and use them to predict with a single classifier on a little bit of data on this 101 categories. So you're using this really complex model, but just with a little bit of data training the bottom layer, the end of the model, the last little bit. So the way this looks like is, here's a cat versus dog 34-layer neural network. At the very end, these things are very specific to cat versus dog. They're like a tail detector, a collar, a tag that says Toto detector or something. In the middle, these are more generic. These are like edges and circles and things like that. And so, can you, if you want to predict 101 categories, can you chop off the end that's very specific, collar, tag, tail, and just plug in logistic regression, support vector machine, any simple classifier to train and predict on this 101 categories where you have just a little bit of data. That's what transfer learning is. And that makes a huge difference. So more specifically, you have to be careful where you cut. So if you go back to this example, if you cut over here, you end up with things that are too specific for car. You end up with a wheel and steering wheel and bumper detectors. So that's too specific. And so you want to use this more intermediate ones. They're more like circles and edges and things like that. So with transfer learning deep features, this is what you get. Start with some label data, not a lot, like we had before. You extract features using these pre-trained neural networks. And we have a lot of pre-trained ones that you can use, or you can pre-train your own. And then you split your data 80-20. You learn a simple model, like a support vector machine. And then you validate. And this time, you can just deploy it in production. No need to iterate, hopefully. It makes life a lot simpler. So let me show you a demo of that. I call it making it doubly easy with these deep features. So more Python code awaits you. So again, I'm going to import GraphLab, and I'm going to load this data set, which is 101 categories, or 10,000 images. And then I'm going to preload a neural network that I trained on that 1.5 million images. So that really big one that we talked about before. And then I'm going to go, for each one of these 10,000 images, chop off the end of the neural network and use it to create 4,096 features per image. They're like circles and columns and things that it detected in the middle. And this is running on a single machine. It just should take a few seconds. So image by image, run it through the neural network in the GPU, compute this 496 dimensional vector for each one of those images. And once I'm done, should be done by now, we can train, yeah, now it's done. We can train a simple classifier. At this point, I'm going to train a logistic regression classifier. So you can go graphlab.logisticregression.create, logistic classifier.create, and it creates a logistic regression classifier on these 4,096 features per image. And this extract features here for the ImageNet model is what I use to make those extractions. And as I said before, when you use it at a high level, we automatically tune in parameters for you in the background. You can also go down, use your own model, tune your own parameters, implement your own. depending on how you use a system like this. But now it's done, and now we have a classifier for this 101 data set, 101 category data set, and it gets about 76% accuracy, which is pretty much state of the art. If I give it a little bit more data, you get about 80-something %, which is exactly state of the art. And you can use it for other tasks. So for example, let me use it for finding similar images. So we have a nearest neighbor algorithm. So I'm going to train it on this 496-dimensional vector for the images. So I just trained it. And now I can make a prediction. So for a particular image, image 50, what are the nearest neighbors? So I'm going to just display it. And you should see the image on the left. You should see the image on the left. Sometimes it's slow, depending on the wireless connection, because it has to transmit the images here. And you see this was the original image, the butterfly, and you see the similar images it finds. And these are images that have similar 496-dimensional features, 4,096-dimensional features in the neural network space. So other butterflies like this. Let's try another example. Hopefully this is a little faster. Let's take the next image. So, find the neighbors, and let's find some similar images. Let's see what happens. I guess the downloading of those images is a little slow in this wireless, because it's downloading, yeah. So, oh, cool. It's a helicopter on the left. Let me make it a little smaller. Helicopter on the, can you see it? Helicopter on the left, other helicopters. That's pretty impressive, actually. That's surprising, yeah. You want to see another one?
Sure.
Yeah, okay. Let's try 250. I actually don't know what it is, but let's try some random number. Image 250. I found the neighbors, and now I'm going to find, kind of select those and display the images. See, this is IPython notebook, and it thinks it's done, so it should be done. Sorry, I'm just not sure why it's not displaying. There it is. Oh wow, that's pretty cool too. It's a chair, with those kind of cool chairs, and a few cool chairs. So it works. All right. So you might ask, these deep features, they got trained on images of dogs and cats and things. How general are they? So as Eduardo was talking about, I'm a professor at the University of Washington, but I also have a company, Dato, and we have a bunch of customers. Here's the most interesting example that I have of image work. It's of our users that I know of. It's a company called Compology. Anybody know it? They put a camera in your trash can, on trash cans, to detect when it's time to empty it. So this is when your trash is full, and it's using deep features to try to figure out how full a trash can is. Pretty cool. I talked about 3 challenges. Let's jump to the last one, which is deploying machine learning in production. This is the last few minutes of the talk. So, data engineering, we're trying to make it simple to deal with terabytes of data, and these are mostly data parallel tasks. The machine learning data intelligence piece, we're trying to make it accessible, and this is not about terabytes, it's about complexity of this computation. So, for example, complexity of image processing. The last one is deployment. This is how you take a model, like the neural network model, deploy it as a service so that I can upload an image and comes back for prediction in real time. And this can be really annoying for a data scientist because you have to talk to the IT organization and tell them, oh, we should deploy my model. And the measure here is not terabytes of data, and it's not necessarily complexity of the model, but it's more about being able to do thousands of predictions per second. And you want to be robust to failures in the underlying architecture. So this is what we call predictive application in production with something that we're going to call predictive services. So let me talk about the challenges there. What does deployment look like? So if you go back to my 2012 view of the world, or data scientist view of the world, you start some data, you run some machine learning algorithm, and you're done. But if you want to build like a cool phone app, then when I query and say every time, give a prediction and so on, how do I do that? Well, I have to take that model that I built in Python, deploy it as a service, talk to some data engineers, DevOps, the app developers, create a custom service for it. And that process typically takes 6 to 12 months. Somebody has to re-implement your Python code, say in Java or C++. When they implement it, it has nothing to do with what you started. The model is now irrelevant because the data in the model has changed. And you have two teams maintaining one system and another system. And I'm a data scientist, machine learning guy, and I feel sad because I want to empower this person, and I want these people to just basically be okay with the data scientists deploying their systems in production. So what would it take, what would you have to build to be able to do that? So you're going to build an app that uses machine learning. And so what you want is a simple RESTful API, REST API that somebody can just query, and then your model is kind of encapsulated in it. Okay, that's a good start. And then you want to be able to deploy as a service. So you need something that's scalable and that's robust, it's fault tolerant. So you have multiple machines and some load balancer, and you deploy a model, maybe one of ours, and if any of these machines fail, that's okay because there's others. And if you have more users at night, you're going to be able to add more machines. If you have less users in the morning, you have to decrease the number of machines, so you're going to be elastic in that sense. And on top of that, you don't want to just, unfortunately, you just don't want to deploy just models that you create from our system, but you also want to deploy anything, any Python thing that you create, scikit-learn, build your own. You want to deploy that as a service. How do you do that? How do you build that? Well, it's not bad. It's you do it yourself. DIY tools you can use. Here's some suggestions. You need a web service layer. Tornado is pretty good if you're a Python person. You need a cache layer. Maybe you can use Redis or something else. You need some logging tools. There's a bunch of them here. You need some metrics tools. You need to piece them together. You need a load balancer. You need to piece them all together. Or, shameless plug, you can use our thing. So let's say you're going to build an intelligent application that uses machine learning, and you're the only data scientist, and you learn this machine learning model. What do you do with it? We have this thing that we call predictive services. With one line of code, you can deploy your model as a service, and I'll show you them with that. So when a user comes to a website and he makes a query, and you want to, for example, recommend a product to that user, you will go to predictive services, query your model, and come back for prediction within milliseconds, and that will save your users. And not just that, if you get new data or if you get smarter and you come up with a new model, you can deploy it with no downtime, and the service stays up. And we can serve anything. We can serve GraphLab Create models, we can serve scikit-learn, we can serve Python, and we soon be able to serve actually other languages as well. So it's just a service that makes it easy to deploy this kind of machine learning models. So this is how we think about deployment, and this is going to be my last demo. And I'm actually going to show you a demo of an end-to-end application being built. So let me talk about the application first. So it's a little bit bigger. So we took a large data set of about 30 million reviews, product reviews from Amazon. And we build a recommender system. So if I say like a particular movie, like Dumb and Dumber, and this is up, yeah, Dumb and Dumber, you will see that it will recommend some other stupid movies by Jim Carrey, Adam Sandler, and so on. You've seen things like this. I'm going to show you how easy it is to build and deploy it, such that when you put Dumb and Dumber in there, it comes back for prediction real time. But let me show you something that you probably have not seen before. Let's say that I love the movie Dumb and Dumber, let's say. But my wife wants me to be a little bit more literary. So she says, you know, you should really read the book Sense and Sensibility. And we're having some relationship problems. And we don't want to spend money in therapy. Couples counseling takes too long. So what can we do? The machine learning model saved my marriage. And so imagine my preferences and my wife's preferences. And imagine forming a graph where you connect two products together if lots of people like those two products. And now you have my preference here, my wife's preferences. Now you can ask, what is the shortest path in the space of products from my preferences to my wife's preferences? So the shortest path from Dumb and Dumber to Sense and Sensibility. I'm going to give this two endpoints. is going to be uploaded to this predictive service, which is, this one is on AWS. You can run it anywhere you want, on-premise, AWS, other clouds. And it's going to come back for prediction. So, we should get, since actually I want census sensibility, the book, not the movie, because that's even more challenging, the book. What is going on? So, yeah, so here's census sensibility, the book. So, start with Dumb and Dumber. Let me just make sure they can read this. Start with Dumb and Dumber, then watch a stupid movie with Adam Sandler. And then Adam Sandler is also in romantic comedies. So you watch Wedding Singer, which is romantic comedy for Adam Sandler. After you watch that, you're ready to watch Clueless, which is another romantic comedy, which you might know, but it's a parody of Emma, which is a romantic comedy based on the Jane Austen book. So right after you watch Emma, you're ready to watch another Jane Austen book, movie, and then you're ready to read a couple of Jane Austen books, including Sense and Sensibility. And this is how you resolve relationship problems. So let me show you how to build and deploy something like this. So I'm going to here. Zero output. Okay. Let's see. How is the font size? A little bigger? Make it a little bigger? Yeah, you're in the front row. Okay, I'm gonna. You guys all know that I have this company Dato, so I can hide that top line there too, right? Okay, so we're going to deliver data science together, and then I'm going to conclude. So last little bit. So import GraphLab. Oh, let me restart the kernel so you don't think I'm cheating. Right? So I'm going to restart everything. Import GraphLab. You should upgrade to version 1.4. Thank you very much. So I'm going to read some book review data from Amazon. And I'm going to read it as an S-frame, which is a column data star that we talked about earlier today. And the first thing is going to do some data engineering. So if you have some data, what's the first thing that you do? Just take a look at your data, see what you got. So let's look at a few rows of the data. So this is book review. So a user reviewed an item. They had a title. They had a price. They had some helpfulness of the review, some score, a date, the text, and so on. Makes sense. What's the next thing that you do? Cut the data this way, that way, summarize it, try to understand what data you have, visualize it. That was getting slow. And so we built Canvas, GraphLab Canvas, which allows you to visualize data and anything that we do. Basically, you can type .show on anything that we have, any data structure, and we come up with a visualization for it. So for the Scalable store, the first thing it's going to do is go column by column and use a sketching algorithm. One pass on the data comes up with a summary. So this is book review data. The most commonly reviewed book is Harry Potter. The average price is $22.56. Highest price $104, and so on. And if you click on a particular column of data, so for example, the summary of the reviews, it gives you a more detailed sketch. So these are book reviews. The most common summary is great book, followed by great book, followed by excellent, good book, great read, excellent, amazing, and eventually disappointing. So in one little visualization, what did I learn about my data? Most book reviews are positive. So if you're non-reviewable machine learning, if you're minimizing squared error, you do a very bad job because everything is good. So you should use a different kind of recommender. So you can choose your own, or you can let us choose one for you. So if you type GraphLab.recommender.create, we will automatically pick one for you. And since the data is mostly positive, we're going to use item similarity, which is a good baseline to get started. So in a few seconds, we should have 11 seconds here, we have a book recommender. We just built one together. So Sean, who works with me, really is a history buff. So we're doing this together, and he really loves the John Adams biography by McCullough. So let's see what other books we should recommend to him. So this is similar items from John Adams biography. What you get is 77. By the way, for those who don't know, John Adams was a U.S. president. So 1776, Theodore Roosevelt biography, Lincoln biography, makes sense. However, if you want to deploy as a service such that every time somebody has a request for a product, you want to come up with those recommendations in real time, you can't have them call you up on your phone, type this in your Python notebook, and then send it back to me. So you want to deploy as a service, right? So how would you do that? So you can either build your own, like I talked about, or you can use predictive services. So I'm going to connect to a predictive service that I have up on AWS. Getting AWS machines takes a few minutes, so I'm not going to do that part. But I can type .show on it and show you what it looks like. So go back to Canvas, and you'll see our predictive service showing up here. And that predictive service is hosting some models, and it has 3 machines. So the distributed system is 3 machines, and they're all up, which is good. So now all I have to do is give the model a name and deploy it. Actually, I had to deploy it when I tested earlier, so I'm going to delete it. It's complaining that I already have it, so let me just delete that. And so, yep. So I'm going to give it a name, Carlos Recommender, and I'm going to deploy it. And so now what happens, and the Wi-Fi here is still too slow, so I might not be able to finish this demo, but what happens is this model that was on my laptop gets uploaded to S3, which is a storage service on AWS, and those 3 machines pull it out and start hosting as a service. There is this robust caching layer on top of it, and now there's a RESTful API that you can call from Python, from JavaScript, from Curl, from anything that you want, that every time it comes with a request, it queries that service, it goes back to your model, queries the model, puts the thing into cache, and comes back to an answer. If this is a faster network, it takes about a minute. It seems like this is uploading slowly, but what you would see is a RESTful API here that I could query and in real time come up with predictions to model. But I'm not going to make you wait here, but at the end, you can come and take a look if you like. So this is where I'm going to plug our platform. So if you want to get started, you can use SFrame and SGraph, which is our highly scalable out-of-core data structures that are available in open source, and you're welcome to use them. But most of our users choose to use GraphLab Create, which includes advanced machine learning algorithms like boosted decision trees, deep learning, data visualization tools, and more. And then when you want to deploy as a service, you have 2 options. You can, if you want to scale to more data, you can use Dato distributed, which distributes the processing and algorithms. And if you deploy as a service, you can query in real time, you can use Dato predictive services. Both of these run either on-premise, on AWS, or other clouds that you might be interested in. So this is what we've been building, and I'm pretty excited about it. We have a lot of users and a lot of brand name companies using it in production today. So it's likely that you've interacted with a service that uses this thing in the back end. So the world is changing. Pretty exciting time to be doing machine learning. Industries are being disrupted. So unless you do something about it, you're going to be disrupted too. It's good for me. So we help you go from inspiration to production, addressing the challenges of data engineering, data intelligence, and so on. Thank you very much. So I don't know how you guys work.
Do you have some time to take some questions?
Yeah, of course, yes.
So, is there going to be markets for these intermediate data sets?
Are there oh, you're talking about deep learning.
Yeah.
Is there going to be a market for pre-trained models?
Yeah.
That is a good question, and I think you will see. I think you'll see markets, pretty interesting markets for pre-trained machine learning models. I don't know if it's deep learning or not deep learning. But you're starting to see some motion out there of companies offering, for example, pre-trained sentiment analysis tools, pre-trained object classification tools, and so. I can imagine that in a few years, there will be opportunities to market those too. But you know, these are just predictions about the future. What do I know? Any other questions?
Anybody else?
Yes.
Thank you,
It's Carlos.
Can you speak to what might be the next thing beyond performance for text mining, other than the bag of words models or sentiment analysis, like you just mentioned? What might be for higher order analysis?
thing in terms of methods, algorithms, or tasks? I think I'm hearing tasks.
Effectiveness, similar to the way a human would read the text.
I see.
And
The question
it's a
here,
bold question,
the bold question,
but you're the person to ask.
but I'm not the person to ask. I see.
Okay.
So no, the bold question is, what is going to take text to the next level?
Yes.
Text analytics, let's say natural language processing to the next level. That's a really interesting question. So I love text data because there's a lot of nuances and complexity in text. And so what would it take to take it to the next level? So from understanding perspective, what I'll be able to, let me tell you what I think would be a cool challenge task first, and then we can ask what would you have required to do that, right? So how many people know about factcheck.org? Political election thing, right? So they take what politicians say and they say, oh, this is true, this is not true, read this article, read this thing, and prove it. Imagine if you could highlight any text on the web and automatically fact check. That would be cool. Anything that somebody says, Eduardo says in his blog post, Carlos sucks, and stuff, so they can fact check that. So the question is, what would it take to do that? That's a really challenging problem. So you'd require combining data from multiple sources, understanding that piece of text, having higher level understanding of what the implications are, having models of how it connects to the different piece of information, and then selecting key ones that help a user reason about that fact. It's not just like the score, you want to get the story behind it. So some things we know how to do today. Selecting piece of information, summarizing, getting the story behind it. There's been a lot of progress on that task. However, being able to fully understand the semantics, like what the person really means and the nuances of what being said, that's going to require much more higher level understanding about language. And there's been plenty of recent work on the topic, some using neural networks actually, some don't. The neural network I think is still too low level, so we need to somehow combine this kind of feature representations, so bag of words, neural networks, parsing trees, and somehow combine with some kind of logical representation of what, kind of how we think about the world. So that's what I think would take, but time will tell. And I don't want to make a prediction as to whether that tool will be built, but I hope somebody builds that tool. Maybe one of you will be inspired and build it. Let me know. There was a question back there first.
Oh, sure. So I thought your work with the pre-trained deep learning system for learning new categories was really cool. And it reminded me in some ways of a paper that Feifei Li wrote several years ago on Bayesian one-shot learning, where basically given a single positive example, learning how to identify that new category. And I was wondering with your system how well you would expect it to perform with that single positive sample.
So by the way, just to be totally clear, if you look carefully at my slides, there are citations to other people's work, right? So I'm just going to be careful that we have a system that makes that kind of thing easier and scalable. And that's our focus, make it simple and scalable. One-shot learning, just to make sure everybody understands it, or what's being discussed, it's a really interesting question, right? So as a human, if I show you one picture of something, a boogaboo, and say this is a boogaboo over here, you're likely to be able to recognize others just from that one image. A computer needs thousands of images.
I hate that analogy. It's not fair because you have so much history.
Exactly.
The computer does it. So it's a false comparison.
So my friend over here hates that analogy, which is good. I like hate. But your point, the reason that what's your name, sorry?
Christopher.
Christopher. Christopher, the reason Christopher hates the analogy is he says a human has so much background information. So the way that Feifei Li's group and others, they were not the first to do partial learning, and others, it says, we're going to introduce that background information. We're going to pre-train models on other types of images, on other types of tasks, cats, dogs, and other things. And then when you take this, use those, say, pre-trained features or pre-trained representations and make it easier to recognize this provable over here. So kind of capturing making the unfair analogy fair. And so I think the pre-trained features that we discussed today would do pretty well at one-shot learning. And of course, that's a statement with no basis, because I'm not basing on anything, but I just believe that, you know, if you look at the models that she was using, some of the new feature representations, and combining the two ideas could do pretty well.
Cool.
So there was a question back there for a second.
So again, on the trained model front, so how do you weigh the balance of how many layers to peel back versus the distance or dissimilarities in the features?
So here's the question. We have this 34-layer model. And do I chop off the last layer? Do I chop off 2? Do I chop off 3? Do I chop off 4? Do I chop off 33? Where do I stop? And the answer is 2. just like everything in deep learning, this is yet another annoying, disappointing parameter that you have to tune. But in practice, observed is that the last 2 layers, they're typically fully connected. They're typically the ones that have the most representation. You call my phone, and then
That's good.
yeah.
We saw on your slides that S-frame was, influenced by pandas. I think it's a very similar interface as before.
Just plug that in.
When you were doing that, that translate concepts to a distributed core environment, were there? Is it like literally a pandas data frame? Like in a sense
It's
of
not, sorry, go ahead, sorry, finish your question.
Yeah, I guess what I mean is that are you like built for that?
Okay. So you're inspired by pandas, which is a data frame for Python, design of S-frame. What out of pandas? So what was interesting to me of pandas, and what I think Wes did extremely well, was some of the API choices that were made. It's kind of the top layer of Python. So that piece we got pretty inspired, and we did something similarly, something slightly different. And their footprint is much bigger, but this design works with PhD thesis, not cheap. So it was a particular data layout, how things got communicated up, like all that stack from the disk representation all the way to the C++ base.
Are there any operations that are differently expensive, that are notably differently expensive in the two worlds?
I see. There some things that are more expensive than other frames, vice versa.
Yeah.
So you have enough data, and performance will be more or less better, or a bit multitask better. But the place where there's enough data, then you have somewhere to make that hands-on design work. So if the data doesn't make it up, if it's in my behave, I'm not going to the past, it just kind of behaves similarly. Other questions?
All right.
Okay. Appreciate you coming out in the rain.
Also, be on the lookout for Big Data Day. I think DataScience.LA.org. That's a full-day conference. DataScience is running a SQL track, and I think it's free. So check it out, Big Data Day, LA.org.